Hi everyone, my name is Rich Cimino and I'm here to present a short video on the topic of my PhD research, which concerns the simulation of chromatography. Liquid chromatography is a commonly used separation technique, employed to separate mixtures of polymers based on their differences in size and chemistry. Chromatography is applied to separations of polymers of all kinds and shapes, including linear and star-shaped polymers, functionalized polymers, and biomolecules such as proteins and enzymes. More recently, liquid chromatography has been proposed to separate nanoparticles based on their size and surface functionality. This short talk will focus on the separation of simple linear homopolymers. However, this methodology I will present may be applied to other cases as well. Chromatographic separation consists of at least three components: a mixture which needs separating, a stationary phase which acts like a sieve to separate the mixture, and a mobile phase which carries the mixture through the stationary phase. Many of you may have performed the experiment shown in the picture on the left. This is a thin layer chromatograph of spinach. In this simple experiment, a spinach leaf is rubbed on a piece of filter paper, the stationary phase. The filter paper is then dipped in water, the mobile phase, which flows up the paper and separates the color-producing proteins in the leaf. While the spinach experiment is easy to undertake, it is less easy to describe the separation process at a molecular level. The main goal of this work is to understand the complex way in which polymers, such as the color-producing proteins from the TLC experiment, behave during chromatography. To do so, we need to introduce some basic thermodynamics. In thermodynamic terms, we describe the polymer's behavior as the competition between entropic and enthalpic forces. Enthalpy may be thought of as the energy of the chain, which arises due to the molecular interactions with the mobile and stationary phase. Entropy is the tendency of the chain to be disordered. When a chain comes into contact with the stationary phase, it gains enthalpy due to adsorbing or sticking to the stationary phase, and loses entropy due to being confined. When a chain leaves the stationary phase, it gains entropy but loses enthalpy. The chromatographic partition coefficient is a function of the chain enthalpy and entropy, and it represents the affinity of the chain for the stationary phase. The partition coefficient is strongly affected by the solvent quality, its temperature, and composition. The value of the partition coefficient provides us with important information on how chains separate. When the partition coefficient is less than 1, chains prefer to remain in the mobile phase and do not interact favorably with the stationary phase. Chains are repelled from the stationary phase according to their molecular weight. This process is illustrated here using spheres of different sizes to represent the polymer chains. Larger coils cannot explore the smaller interstices between particles, and they bypass much of the column porosity. By contrast, smaller chains may explore all of the column porosity and thus take much longer to escape from the column than their larger counterparts. The chromatographic regime corresponding to these conditions is called size exclusion chromatography. In the opposite case, when the partition coefficient is greater than 1, chains prefer to remain adsorbed in the stationary phase, with higher molecular weight chains being more likely to remain adsorbed than smaller chains. Thus, longer, more massive chains take much longer to escape from the column than their smaller counterparts. The chromatographic regime corresponding to these conditions is called liquid adsorption chromatography. Of special interest is the condition at which the enthalpic and entropic forces on the chain are balanced. At these conditions, the chain is equally likely to be adsorbed or to remain in the mobile phase. Because the forces on the chains are balanced, all chemically similar chains will elute at the same time. This behavior can be helpful for us if we wish to separate chains based not on their molecular weight, but on their chemistry. This is often accomplished by altering the mobile phase composition during the chromatography run, such that the critical conditions for each chain are passed. In all of my work, I utilize a simple model chain, a schematic of which is pictured here. The chain consists of a linear string of beads which are the size of several real polystyrene monomers. The beads are connected to their nearest neighbors by springs. The beads, which are not physically tethered to one another, also interact by van der Waals forces. We do not consider an explicit solvent in this model, and as such we must introduce the effect of adsorption explicitly. This is accomplished by introducing an attractive potential well along the stationary phase surface and in pores, which is the width of one bead. The challenge then becomes finding the adsorption potential, which captures the correct behavior of chains at critical conditions. At critical conditions, a chain should be equally likely to be adsorbed or to remain in the mobile phase. By varying the adsorption potential U, we can find the critical conditions. When the adsorption potential is very strong, as shown here, the chain will remain strongly adsorbed in the pores of the stationary phase. In the opposite case, when the adsorption potential is removed entirely, chains will fly away from the stationary phase and remain in the mobile phase. Closer to critical conditions, the chains remain weakly adsorbed in the pore and on the stationary phase surface. At critical conditions, the chain is equally likely to remain in the mobile phase or on the stationary phase. As you see here, the chain may alternate between surface adsorption and adsorption in the pore in equal amounts. This work has been funded by the National Science Foundation and the Rutgers Engineering Resource Center for Structured Organic Particulate Systems. All experimental data shown here were collected at DuPont's Analytical Chemistry Laboratory in Wilmington, Delaware, under the supervision of Drs. Efim Brun and Chris Rasmussen. If you are interested to learn more about this topic, feel free to contact us for links to our recent publications.